All right, we'll get started here. Um, did you guys see the announcement for the MESA program?
Yes.
Okay, so if you're interested, that starts today at 12, but you have to pre-register. So check it out on Canvas.
Is that the only time slot they have for it?
Monday and Wednesdays, yeah. Yeah, something like that. One, yeah. They said that both in person and remote, so maybe their sessions are recorded. I don't know. Worthwhile too. All right, so what did you guys get for this one here? KC. Okay, in this case, we don't have to use activities because it's a KC. So specifically, we're going to have to use, because activity of a gas could be pressure of the gas. And so if it's specifically KC, then we only use concentration. So
the bracket is mean activity?
No. The bracket means molar concentration.
Even if it's a gas, you don't use partial pressure.
We don't use partial pressures. Even if it's a gas. If it's a KC, we have to use the concentration. So this is defined usually as moles per liter or molarity, molar concentration. The activity is going to be given as this, little a will be for the activity. The activity will approach the molar concentration at infinite dilution for solutions. Infinite dilution is, it just means the more dilute the solution is, the more ideal it behaves in terms of things. Activities related to the effective concentration. And the effective concentration changes depending on certain things. There's some very specific examples of this. So one of them would be have you heard of dimers? Dimerization. Let's say you made a 1 molar solution of this. This would be benzoic acid. You made a 1 molar solution of benzoic acid. This is a benzene ring with a carboxylic acid group on it. The effective concentration of this is like a half a molar. Why is the effective concentration of this like a half a molar? Or it depends. Even if you're looking at acidity, it could even be lower than that. And the reason is because of this dimerization. So a lot of people write the benzene ring shorthand like this, and then do the same here. So we have this, but what happens is that we get 2 of these things lined up. And the way they line up, they optimize the hydrogen bonding interaction between the two. And it forms a good, strong, hydrogen bonding interactions are like 25 kilojoules per mole. What are covalent bonds, roughly? Covalent bonds range from what to what energy? Like 60, 100, 600, 1,000, million? What do covalent bonds range from in terms of energy? We don't memorize the whole chart, but usually what we do is we memorize the limits. You don't memorize every tree in the forest, but maybe you memorize what's the biggest tree in the forest. You know, 3,000 feet, 100 feet, 10 feet. What's the biggest tree in the forest? You know, if somebody said, "Oh, the biggest tree in the forest is 30,000 feet," what would you think? No way, right? But people often say, "Oh, yeah, the bond energy, oh, that's about 30,000 kilojoules per mole," and then people are going, "Where's this guy coming from?" You know, definitely not from this universe. You know, and so that's why you need to have some kind of reference points memorized. You know, you don't memorize the whole thing, but you memorize certain things like fluorine. You know, fluorine's the most, electronegative, and things like that. Fluorine's the most electronegative. What's the least electronegative? Not lithium. Close though. Francium. Francium's radioactive, so very people pay little attention. Its half-life is very short. It doesn't live for very long. So usually people talk cesium. You know, if francium could live long, then it would be, you know. So cesium. Okay, what the electronegativity of fluorine is 4O. What's electronegativity of cesium?
Isn't cesium radioactive sometimes too?
Yeah, there's isotopes of cesium that are radioactive, but there's stable isotopes of cesium as well. In fact, there's radioactive isotopes for a lot of those elements there. So you don't memorize every single electronegativity, but you should memorize two, you know, fluorine and the least. That way you have a range. You know, what we want is some kind of mental range kind of thing, and that's helpful. And so, you know, a lot of people say, that's memorization, but you know, it's very helpful to have some things memorized. Like that way, if you come up with some number, oh yeah, the electronegative cesium is, I would think 150. Would you know that's terribly wrong, or does it sound right? You know, or you have no idea. You know, and so anyway. So typical covalent bonds range from, on the low end, a little less than 100 kilojoules per mole, to the high end. You know, what's the strongest covalent bond that you can think of? Well, hydrogen bonds are thought of as intermolecular IMFs, intermolecular forces, not real bonds. You know, real bonds would be like covalent and ionic bonds. Covalent bonds typically range from less than 100. You know, there's some very weak bonds because under 100 kilojoules per mole can be broken by visible light. So like iodine, you know, iodine's covalent bond's pretty weak because it's big iodine atoms. So if you have iodine, you don't store it in a clear container, you know, because if visible light hits it, it'll break the bond. So we store it in a black or brown container, like hydrogen peroxide. Hydrogen peroxide's, you know, bond energy is less than 100 kilojoules per mole. Visible light can break that easily. And so hydrogen peroxide is stored in brown bottles. You know, you can't see through them. So anything like that, you know, we got to worry about because visible light goes up, you know, to about 100 kilojoules per mole, maybe a little bit more. Well, anyway, those types of things, they're kind of nice to know. Like probably the strongest is the triple bond, right? Which is around 1,000 kilojoules per mole. And then we know some lattice energies. You know, lattice energies could go well above that. You know, lattice energies at 2,400 kilojoules per mole or greater. Well, anyway, you got two of these, and so that's like, you know, just roughly 25 kilojoules per mole. That's like 50 kilojoules per mole to break. That's starting to approach a weak covalent bond, and so these are really stuck together. And so this is called dimerization. And so what happens is these benzoic acids pair up. They pair up, and what happens is they aren't going to be very, very effective or as effective in terms of numbers, as you might think. And so, I remember this one very well because when I was a teaching assistant at UCSB, there was a question on the Chem 1A exam about dimerization. I thought, wow, that's pretty interesting. They're talking about colligative properties and dimerization. So the question was, I think it was benzoic acid, why are the colligative properties of benzoic acid so far removed, so far off from what you would expect, based on its mole concentration, something like that. And so they had to come up with dimerization and then write a little thing about dimerization, basically. These are like, when you have these carboxylic acid groups, so this would be benzoic acid dimer right here, which is very, very common. So images. There's a Wikipedia thing on dimerization. We have like monomers, trimers, polymers, dimers, etc. Sometimes they bond together, sometimes they're held together by intermolecular forces. But the activity, this is for solutions here. And so the molar concentration of benzoic acid and the activity of benzoic acid will be totally different things. But for most things, they don't have these very strong, that's a very strong intermolecular forces of attraction. So for most things, we don't worry too much about the activity deviating from the molar concentration significantly. And we try to keep this is why, when we're doing pH calculations, we try to keep it between 0 and 14 so that the calculations are reasonable. Once you go below 0 and above 14, then the calculations are going to be way off, because we're not factoring activity, the effective concentration. But it's easy. Actually, factoring in activities is easy to do. It's just one extra step. And so they talk about activities in our book, but they don't actually make us do any calculations with activities. But it's not that hard, but they're trying to keep the level of complexity down. They don't want to add too many things. And so, like, if you were to continue on in like, say, chemistry, the next class you take, after organic chemistry, you'd be doing activity calculations and you'd be doing this kind of stuff, for solutions. But what we try to do is we try to keep the concentrations low. If we work with low concentrations, that's why when you look at a lot of things we do, it's like 0.100 molar. 0.100 molar is not that concentrated, right? But that keeps things working nicely, versus like 12 molar or other things, which would make things a bit more of a headache to deal with. Even our calculations, though, sometimes if there's strong interactions like this, even if you're at 0.100 molar, there's probably significant diionization for this. Or if you're dealing with large, high-charged ions, if you're dealing with high-charged ions, then you're going to expect deviations, significant deviations from activity and the stoichiometric concentration. So what we're going to do is we're going to completely ignore activity. We should know what it means, and we should know that our calculations could be off because we aren't factoring in activities. But we're just going to make the assumption that, we're working with fairly dilute and that the inter-ionic, intermolecular, whatever attractions are going to be weak. Now, if we were to do the activity of this one, these are all gases. And gases we would do by pressures, and we already know, like, what would you rather use? Would you rather do van der Waals calculations for gas, or would you rather use ideal gas law calculation? Ideal gas law, that's a lot easier. And so for gases, same thing, but here they're asking for Kc, so we can't use activities for this. We want to. And so we'd have the concentration of NO2, which I put in square brackets, the molar concentration. Now, this is agreed upon. So if we see a Kc value, let's look at for a Kc value. If I see a Kc value here, it's 2.1 times 10 to the 30th. They use the molar concentrations. We know that for sure. If we see the Kp value, then it becomes a little bit more tricky. Because if we use the Kp value, did they use atmospheres or did they use, what's the other one? Atmospheres or did they use bar? We don't know that, actually. It depends. In the US, you would expect them to have used atmospheres because US, you know, is more, I guess, as far as adopting metric type things is more well, anyway, U.S. likes atmospheres, and it makes sense. Atmospheres make sense because, you know, what's the average pressure at sea level? You know, 1 atmosphere. The average pressure at sea level isn't 1 bar, it's 1 atmosphere. But fortunately, 1 bar is close. You know, they're not terribly different. And so you'd have like a 1% error, you know, if you use bar by accident when you're supposed to use atmosphere, you know, around, you know, a few percent, maybe less, depends on the calculation. So that's one thing we have to keep in mind. Did they do this using bar or did they do it using atmospheres? So we'll have to keep that in mind. But anyway, what we're going to have here is this concentration of NO2 squared divided by the concentration of NO squared and O2. How about this one? What did you get for B? Concentration of zinc metal or zinc ion? Zinc ion.
Over concentration of silver squared.
Yeah, good. And then we leave out the solids. We have an activity of 1. C? What did you get for C? Concentration of hydroxide squared.
Over concentration of CO3.
Yeah, carbonate to the first. Good. Okay, how about KPs here? What did you get for A?
The partial pressure of CH4 gas times the partial pressure of H2S squared over the partial pressure of CH2 gas times the partial pressure of H2 to the 4th.
Yeah, good. That's good. You know, one of the most common errors is that people forget to raise it to the power of 4 or forget to square it. You know, this is a common error. That's good. What about this one?
Right, are we supposed to still raise it to the power, or do we just do times rate of temperature to
The RT, I mean, what was that? The rate?
or sorry, not the rate, yeah, the RT to the RT raised to the.
Okay, you're saying that the delta N of gas here, what was delta N of gas? So we're going from 5 moles of gas to 3 moles of gas? The delta N of gas would be -2 for this one. But in this case, though, no. Because there are 2 ways we could get the Kp expression. One is we could do the Kc, that is the concentrations. And so if we did the concentration of CH4 times the concentration of H2S squared, so methane, hydrogen sulfide, divided by the concentration of this is called carbon disulfide, which is normally a liquid, so this must be a higher temperature. Divided by if we did the concentrations, then we would multiply by RT, quantity, delta N of gas, if we did the concentration. But since we're doing Kp, we don't use that there.
Can you write the answer out?
This one? Yeah. So partial pressure CH4 times the partial pressure of hydrogen sulfide, so methane, hydrogen sulfide. So hydrogen sulfide is going to be squared divided by the partial pressure of carbon disulfide times the partial pressure of hydrogen gas. And this is going to be to the fourth. Yeah, that would be it. This would be Kp. Well, let's answer the question. Is our book going to use bar or atmospheres? Now, considering the authors are Canadian, what do you think they're going to use? Bar, right? And so they're using bar. I still like to use atmospheres and then convert things to bar, but okay. If the number of moles of gas on the top and the number of moles of gas on the bottom are the same, then it doesn't matter. I could use bar or atmospheres, I'm going to get the same ratio. It's just when the number of moles of gas differ from the top and bottom that I can't use that because it doesn't quite work out. Okay. How about B? What did you get for B?
To the 1/2.
Yeah, partial pressure of oxygen to the 1/2. Now, let's say we reverse this. What would if I reverse that reaction, so let's say I'm oxidizing the silver. Silver is really hard metal to oxidize, but let's say I have silver solid plus 1/2 O2 going to silver oxide solid. What would this be? What would Kp for this be? Yeah, that's good. It's 1 over the partial pressure of O2 to the 1/2. Okay, let's look at C. What do you get for C? Here, states are very important because H2O could be a liquid or it could be a gas. It could be a solid too. In this case, it's a gas, and it makes a difference in the Kp expression, obviously.
Kp equals CO2. The partial pressure of CO2 times the partial pressure of H2.
Yep, that's good. That's correct. Okay, let's move on to 5. Write an equilibrium constant Kc for the formation from its gaseous elements of 1 mole of HF. And so here we're doing formation reactions. Do you remember the definition of formation reaction? So for example, you did formation reactions, delta H sub F, with this little superscript. And so what was the F? F stands for formation, and how is formation defined? Yeah, but there's more to it. There's more restrictions to it. What's the other restriction? So we're trying to form HF.
Has to be formed with hydrogen gas and fluoride.
Well, yeah, it has to be formed from the elements in their most stable state under the conditions. So, and its formation is defined for formation of 1 mole. And so when we look at delta H of formations are compiled in Appendix D. When we look at delta H's of formation, they're always for 1 mole. So this is not technically a formation reaction. This is 2 times the formation reaction because it's 2 moles product. Same thing here, 2 times. This would be 1. So these ones we could look up in Appendix D. These 2, we double what we find in Appendix D when we look at the formation for those, if we're interested in delta H formations. So I just wanted to make a note of that for this because of formation. technically A is fine. So A is for 1 mole HF in the gaseous state, and this is going to be formed from H2, and this normal state is gas, and F2, which is normal state is gas. So we're forming 1 mole of that, and so what are the coefficients to balance this? Yeah, this is going to be 1/2 H2 and 1/2 F2. And so K, what do they want, KC or KP? KC, what is going to be here?
It's gonna be HF over, the concentration of H2 to the 1/2 times the concentration of F2 to the 1/2.
Yeah. Good. B. This formation reaction is pretty common. It's given a name. So we're going to form 2 moles of NH3, so 2 NH3 gas. And we're going to form it from what? Yes, nitrogen gas and hydrogen gas. So let's balance it. Yeah, 3 in front of the hydrogen gas and then it's balanced. Okay. You know, I was talking about like the 10 most significant reactions in modern civilization. You remember that? This one is another one of those. This one is the it's given a name. What's the name of this? Born-Haber. Is that right? The Born-Haber reaction. Let's see. This is Born-Haber. Born-Haber cycle. What the heck was this reaction called? I should know, but okay, that's just balancing. This one's not too hard to balance. Significance. Yeah, Born-Haber process. Anyway, this was huge because we need nitrogen fertilizers. And so this reaction, which produced ammonia, which is used for fertilizer, increased the food output, I think, tenfold at the time, which meant that, you know, so many fewer people starved to death, basically. And so world food production dramatically increased. So this is why it's such a significant reaction. But why don't you just inject nitrogen into the ground? You know, nitrogen, because the fertilizers contain nitrogen. And so just inject nitrogen's in air, it's 70%. 78% nitrogen, right? Air is. And so what isn't just nitrogen? Why don't plants just take, certain plants do take up nitrogen. You know, beans, legumes take up nitrogen, but all other plants, they can't do what's called fixing nitrogen. Because why? Why is nitrogen so hard to fix? That is, why is it so hard to react?
It takes too much energy for organisms to incorporate it into their.
Right. This bond is tremendously strong. This bond is about what? How many kilojoules per mole is that bond?
1,000.
1,000 kilojoules per mole. Good. That's 1,000 kilojoules per mole. It's too much to break. In fact, this reaction really doesn't happen. You know, what Born-Haber did was they got this reaction to go. They got this reaction to go with a combination of Le Chatelier's principle and catalyst, you know, to speed it up. But this is a terribly slow reaction and terribly difficult reaction to do. And so they did this under conditions of, that's pretty interesting. They did it under high pressure or low pressure? They did it under high pressure. Now, temperature, did they do it under low temperature or high temperature? And so what we need to know is, this. You know, which direction is exothermic, which direction is downhill? And then we can figure it out. Well, if we have the delta H for this, then we can tell easily. But we don't have the delta H for this, unless we go to Appendix D. If we go to Appendix D, that's so simple. We just look up if it's negative or if it's positive. But sometimes we just kind of think about this. You know, what are most delta H's of formation? Are they mostly exothermic or mostly endothermic? So these are certain patterns that we look for. When we're looking at tables. Most people, when they look at a table like this in the center or the table on the left, they say, forget it, it's too much. They don't look for any patterns or do anything with it. If you look for patterns in that, and you can see some patterns in that, then you're way ahead of everybody, because most people don't give it a second thought. And if you ask anybody about those, they can say nothing about them, you know, because they don't know anything about them, right? And so you would be, you would make an impression, basically, if you could say something. So if we look at most of the delta H's of formations, you see. So one of the things I look for when I look for a table like this, with delta H's of formation, actually, Petrucci likes to put the F after the delta. I like to put it after the H, but it doesn't matter. You notice some are 0 delta H of formation. Do you know why? A lot of these are 0. Well, it's pretty easy. Right? And so oftentimes. But you look at most of these delta H of formation, are they mostly exothermic or mostly endothermic? Exothermic. So usually when we form compounds from the elements, compounds are more stable. This is why compounds form. Otherwise, the world would consist of elements alone. You know, how stable is hydrogen as an element? You say hydrogen exists, you know, what percentage of air do you think is free hydrogen gas? You know, next to nothing, right? Why? Because hydrogen isn't so stable. Right? But then again, hydrogen is a reducing agent. Nitrogen is what we call an oxidizing agent, but it's not the greatest oxidizing agent. Nitrogen, we don't worry about things being, you know, what's it, oxidized, or what would you say for nitrogen? Nitrodized? Nitrodized? Do you worry about things being nitrodized? No, because nitrogen is not a great oxidizer, unless you're dealing with like lithium. If you have lithium metal or some of the other very reactive metals, then watch out, because you could have reaction with such a weak oxidizer as nitrogen. It's a weak oxidizer because that triple bond, right, kind of makes it like that. But yeah, when you look, you know, one of the simplest patterns you see is like, wow, so much negative, you know, which is exothermic. Appendix D stretches on for a long. Some of these are positive, but it kind of makes sense why they're positive. You can see a pattern why they're positive. Like, for example, atomic fluorine has a positive delta H formation. Does that make sense? Yeah, because atomic fluorine is less than an octet. That's what's called a free radical. It's got that dangling bond. It has 7 valence electrons, right? It's not going to be so happy. Same thing with atomic hydrogen. You know, it doesn't have the duet. So some things are positive. Well, HCN gas, that's kind of interesting. I wouldn't have expected that. Yeah, HI gas, which is another positive. Well, so we look, so most likely it's exothermic, and when we think about hydrogen, hydrogen's not so happy alone. So let's take a look at, we can take a look at ammonia here. So if we look at ammonia, ammonia gas, ammonia aqueous, we have, these are going to be different energies, but ammonia gas is minus 46, so exothermic. So if it's exothermic, think about this. Freezing ice or melting ice, which one is exothermic? Freezing ice. Freezing ice, high temperature or low temperature? So if you want to freeze ice, you could do it at low temperature. Exothermic reactions, you want to do at low temperature. So if this is exothermic, you want to do this at low temperature or high temperature? You want to do this at low temperature. So, okay, this would be an easy Chem 1B problem. An easy Chem 1B problem, you're given delta H. A hard Chem 1B or harder Chem 1B problem, you're not given delta H. You have to figure out, what do you think is delta H for this, positive or negative? If it's oxidation, like oxidation, they're all exothermic. Those are all favorable. Iron, rust. Except for gold. Gold oxidation would be endothermic because gold doesn't like to. Platinum would be endothermic, right? Those would be endothermic. So oxidizing nitrogen, forming oxides of nitrogen, you'd expect to be exothermic, but there's a tug of war there. Nitrogen wants electrons, oxygen wants electrons. Nitrogen's electronegativity, oxygen, the fluorine's like a 4O, oxygen's 3,5, nitrogen's like a 3O. 3O versus a 3,5. They're pretty close. In fact, the three most electronegative elements on the periodic table are fluorine, oxygen, and nitrogen. And so here, when we try to oxidize nitrogen, so this is formation, this is taking N2 and O2. That's a good thing, though, because NO and N2O, well, N2O, NO is toxic, right? Nitric oxide. Well, I don't know. It's not, nitric oxide is important for your body. Otherwise, your blood circulation doesn't operate. So, but if you inhale too much of it, it is a toxic. These are oxides of nitrogen. You go get your car. If you have a car, you got to get smogged. They check for oxides of nitrogen or NOx. You don't want too many NOx formed because that's going to create a lot of pollution and emit toxic gases, obviously, in air. But it's a good thing. Nitrogen and oxygen don't react. Why? Because nitrogen's got that very strong triple bond. But you can get NOx formation at very high pressures and high temperatures that happen in combustion engines. So gas vehicles, like regular gasoline vehicles, will produce NOx. But diesels produce even more NOx emissions because they operate at much higher pressures, in the combustion chamber. And they have a lot higher NOx emissions. And another thing, if they really want to do something about pollution, then what they should do is they should regulate or put more pollution control devices on diesels. There are a lot of diesels still driving around. Obviously, commercial trucking and commercial shipping, they use diesel engines, and there's very little emissions control on those. So I think, there are things to do before, forcing everybody to invest in electric vehicle. I think, electric vehicles are great because right now, gasoline prices have skyrocketed, but electricity prices have only gone up like 20%, compared to 100% for gasoline or something. So electric is still pretty cheap. In fact, I drove electric vehicle from LA to Santa Barbara, and it was probably only $10, electricity or something like that, $12 in electricity. It's just amazing how much cheaper it is, versus I have a gas guzzling vehicle, which would be like, $60 for that same trip. You know. But electric vehicles are expensive, and then, to install, did I tell you how much it cost to install the electric thing at the house? It was about $3,000 because I got a permit, for it, and then inspection. The city came out to inspect it to make sure it was on the proper breaker, and then the installation, and then the charging thing. Actually, it was a little more than $3,000. But I just think, if the goal is to, cut down on pollution, well, maybe the goal is also to cut down on fossil fuel usage, but, there are other things we could do, maybe would be more cost effective. Okay, so, those are going to be endothermic, but the nitrogen, nitrogen. Nitrogen's tough to react. In fact, this is why this reaction was so historic, because they figured out to do this at high pressure and low temperature to maximize the yield. The yield still wasn't very high. I think the yield was still like 60% yield or less, maybe 40% yield, but that was still way better than what you can get, under normal conditions. So we need this. This semester, we're going to add delta G and S to the mix. So you need to know this stuff very well. What does this symbol mean, that little superscript? Define it for me. Okay, and then there are others, other things. How does enthalpy and internal energy, what's similar between enthalpy and internal energy, and what's different between internal energy and enthalpy? Internal energy has the symbol U in our book. So what's the difference between delta U and delta H? Do you know the difference? Okay, you'll need to review this. This is back in chapter 7 or something like that. You'll need to know that, because if you don't know the difference between a delta U and a delta H, then you're going to struggle when we hit delta G and S. So think about that for reviewing. And then CP, do you know what CP is? Well, C is specific, the symbol for not specific heat, the symbol for heat capacity. And P is just for constant pressure. So it's the heat capacity at constant pressure. And so heat capacities were talked about way back in that chapter as well. So you need to review heat capacities, all that stuff would be good to start. We still have time, but thermodynamics, thermodynamics is a tough topic. In fact, thermodynamics is this topic called Chem. And they sell bumper stickers. I passed Chem. They sell these at UCLA, I think. So I saw this. Somebody gave me one of these. I have it sitting in my office. Honk if you pass Chem. And so you can buy these because the failure rate is so high, it decimates the class. It decimates the class because they don't know the definitions of everything, and so they end up using the wrong equation under the wrong circumstances. It's like, no, you can't use that equation, and the conditions are wrong for that. And so you have to keep track of all those things. And if you don't keep track of all those things, then you're just lost. It's like this table on the left here, just lost, And so that's what you got. So, one way is we just build up slowly. You know, we build up slowly, so we just go back and figure it out. If we don't know what these things mean, and we figure out what those mean, then it's not so hard. So I postponed this topic is chapter 13, but I'm postponing this till later. You know, we're going to come back to chapter 13. This is why when we hit chapter 15 and they're talking about activities and some of the thermodynamic stuff, we're going to kind of gloss over that and come back to it. Okay, so here, this is dinitrogen monoxide or nitrous oxide or laughing gas. So this is formation of 2 moles of that. 1 mole of ClF3. So after you do the number of these, then it doesn't become so complicated, right? And then we have the KPs for these: 1 mole of NaCl, 2 moles of ClNO2, 1 mole N2H4, 1 mole of NH4Cl. And we could do 1 mole of NH4Cl. This is going to be solid ammonium chloride. And so we're going to form this from what? Well, what are the reactants? Not NH4. Nitrogen gas. It's weird, isn't it? It's weird to form this from nitrogen. You can't just take nitrogen gas and mix it with, what are we going to mix it with? Yeah, hydrogen gas and chlorine gas. We can't just take a lighter and mix a nitrogen, hydrogen, and chlorine, take a lighter and ignite it and expect it to form ammonium chloride. It just seems kind of ridiculous. But there's a reason for this. The reason why we use formation, do you know the biggest reason why we use formation reactions? The biggest reason why we use formation reactions, even though this reaction is kind of ridiculous, you wouldn't expect it to go, is because of Hess's law. Hess's law becomes so much easier if we use formation reactions, because normally Hess's law is you got to cancel things out, right? But if you use formation, you don't have to even write any equations out. You just take the delta H of the formation of the products minus the delta H of the formation of the reactant. It's so simple, the calculation. And so if we use formation reactions, that just makes our life so much easier in terms of Hess's law. And so this is a Kp. So what is Kp equal to here?
One over the partial pressure and 6 to the 1.5 H2 gas squared of partial pressure of CO2 to 1.5.
Okay, great. Now, okay, so we've done these things. Now what we want is we want some numbers here. So how do I get the numbers for this? Equals what? And so, in order to get the numbers for this thing, what we have to do is we have to actually do this reaction and then measure these. And so we have to measure the equilibrium partial pressures here when they're in equilibrium with solid ammonium chloride. So the reaction has to go and we have to measure these things. If we measure these things, then we plug those in here, and then we can calculate what our K value is. And so let's take a look at determining K's. Well, fortunately, somebody else did the measurements. And so determining K values. So one way is to measure the equilibrium concentrations or pressures. And then just plug it into the equation and calculate it. And so we can measure it. This is experimental. Right? So determination of K. But do you want to have to do that for every, I mean, it's not so easy to do. Right? This is, but a lot of them have been done this way. And since lots have been done this way, then it gives us to the second method. Just look it up in a table. Because somebody else did the work, and so all you have to do is just copy it off the table. The next way we could do it is by calculating it. Calculation given the K table. And so there are two types of calculations that we do. One calculation is like Hess's law, but it's Hess's law for equilibrium constants. It's not Hess's law for energies, delta H, delta U, delta G. Or we can calculate using KC, KP conversions. And so let's look at KC, KP conversions first. So I will call this KC, KP. And so here we're given a value of KP. And so they measure the partial pressures of these at equilibrium to get the KP. What if I want to do KC? Do I have to redo the experiment and then measure the concentrations? No, I don't have to redo the experiment. In fact, I could just use a relationship between pressure and concentration for gases here. And so let's go ahead and do that. And so here the equation is Kp, pressure is equal to mT over V, in other words, the molarity. Kp is equal to Kc, which contains the molarity over volume, not molarity, moles over volume, so N over V times RT. RT is going to be raised to the delta N gas. And so I don't have to repeat the experiment, I can just calculate it. So here we have a Kp of 2.9 times 10 to the minus 2 at 303 Kelvin. And so let's do 7 to 8 here. There's no units on Kp, there's no units on Kc. These are dimensionless. They're dimensionless because activities have no units. And we really should be using activities. And each K has a specified temperature. This temperature is going to be 303 Kelvin, 303 Kelvin. Okay, so then we'll just plug it in. And then we'll solve for Kc here. So Kc is going to equal Kp divided by RT to the delta N of gas. And so Kp, we know that was 2.9 times 10 to the minus 2. R, which R should we use? Should we use the ideal gas law R, or should we use the other R, 8.3145 joules per mole Kelvin? Thermodynamic R. The ideal gas law. The ideal gas law, I know that I have it memorized for atmospheres. Do you have it memorized for atmospheres or bar? Both? You have it memorized for both? I only memorized one, and I memorized 0.08201 liters times atmosphere per mole times Kelvin.
After the RT, it says delta what?
Delta N of gas. Delta N of gas. Okay, now, if I'm working with bar, I know the conversion from bar and atmospheres. I have that one memorized too. Do you know it? Okay, a bar is a little bit smaller than an atmosphere, so it's 1.01325 bar per atmosphere. And so the atmospheres cancel it into a bar. So it's only, like 1%, 1.3% different. And then T will be 303 Kelvin. And we don't really worry about the units. We don't really worry about the units. But we make sure we use the right ones, in here. And so then we can calculate it here. So I'm going to do 0.029 divided by 0.08201 divided by 1.01325 divided by 303. And so I'm going to get 0.00115. How many sig figs? I'm allowed 2 sig figs, so I'm going to get 1.2 times 10 to the minus 3 for my Kc. Assuming I did the calculation correctly, that's what we get. Except I blew one thing. I screwed up one thing. What did I screw up? Delta N of gas. Shoot. What was delta N of gas for that? Yeah, delta N of gas is we're going from 1 to 2 moles of gas. And so is that plus 1 or is that minus 1? It's plus 1. So we're gaining 1 mole of gas, it's plus 1. So I got lucky. Because my delta N of gas is just 1. And so I don't have to redo my calculation unless I screwed it up.
If one of the products was a solid, would you not include that?
Yeah, we can't count it. So let's take a look at delta N of gas for B. What's delta N of gas for B? Yeah, we're going from 3 to 2. So that's -1. We're losing 1 mole of gas. So delta N of gas is -1. C, what's delta N of gas? So we're going from 4 to 5. That's going to be plus 1. 8A.
Sorry, we include the solid.
Oh, no, we don't. Yeah, we don't. Sorry. So we're going from 4 to 3.
3 to 3.
3 to 3? Oh, yeah, we can't include this one either. So it's just 3 to 3, which would be 0. So delta N of gas is 0. So this one's easy because if delta N of gas is 0, then Kp and Kc are the same. Right? So if this is 0, this term goes to 1, and Kp and Kc are the same. And so we don't have to do any calculation for this one. Kc is 0.429. (8A), what's delta N of gas? Yeah, plus 1. 8B, plus 2. 8C, going from 3 to 5 plus 2, right? Plus 2? Okay. And then we just plug it in to that equation over there and just solve for the unknown. Yeah. Straightforward. Okay. Maybe I didn't do this right, because look at number 9. If we take a look at number 9, the vapor pressures of water at 25 degrees C is 23.8 millimeters mercury. Write Kp for the vaporization of water with pressures in atmosphere. What is the value of Kc? So they're saying Kp in atmospheres. If Kp is in atmospheres, then I don't need this factor. And so just, if it's not clear, then we don't know.
What should we assume?
Well, let's take a look at what we should assume, because that should be in the book. And so let's take a look back in this chapter to take a look at Kp. Kp 15.2. Oops. See what they say here. Actually, we need to go one page before this.
It says,
Out of time. Let me just finish with this. To evaluate K, we can express the pressures in any pressure unit, but using a unit other than bar requires an extra calculation. So bar is the standard, right? That is the evaluation of the factor. If we express pressures in bar, then this factor has a numerical value of 1. And so the bar makes the activity and the pressures a little easier to deal with. So that makes sense why they're using bar. However, if we choose instead to express pressures in atmospheres, then what we need to do is we need to use this conversion, 101.325 conversion here. And so it's in bar. So this is correct here because it's in bar. The other one they gave us, I don't know what they're doing. Maybe they're asking us to do it in atmospheres. And so we have to specify that this is in atmospheres against what the standard is. Are we out of time? Yeah, all right, let's stop here then. Figure out.